So, second video for exercise phys and relating it to a topic. So what I did for an exercise today was just a really fast arm day, consisted of bicep curls, shoulder presses. Well, it was arms and biceps and shoulders, shoulder presses, shrugs, military press, and hammer curls. So where that one relates into our contents would be, in particular, I don't have anything heavy. I'll just use this bottle. So for a contraction to occur, there's an optimal length. So if it's all the way, my arm is fully extended to this length, I would have less overlap between my actin filament and my myosin filament. So when I contract from here, well, technically it would be like here. So if I would try to contract from here, with this being a isometric contraction, I believe, where there is no lengthening or no shortening, there's going to be less of a pull here as opposed to here, because there is a more overlap of the myosin and actin filaments when it's slightly contracted, because remember, they are a sliding filament. So if they are fully stretched out, technically it wouldn't be that excessive, because there will still be a good amount of overlap even when my arm's like this. If my elbow went like more downwards, so like this was lower like that, it would have significantly less. But because of just how the body is structured, it's going to have enough of an overlap at this length to be able to provide a strong contraction. But the strength of the contraction at here, I feel like I just rambled all of this. So let me clarify. So my contraction right here would be less than my contraction right here at this length, because of the overlap of the myosin and actin filaments. So, however, there's also a upper limit to that. So my contraction when my arm is like this would also be less than if my arm was like this. Now, I don't know the exact optimal lengths for the arm just off the top of my head, but this is a generalized statement using my arm as an example, because when my arm's like this, I try to contract, there's going to be an excessive overlap. So there's less room for the muscles to go. So this really only happens when the muscle cells are very, very compressed within each other. So maybe something like a heart cell, where there is no more room for the myosin and actin filaments to slide past each other. So there's going to be less of contraction, as opposed to right here, which is more so the optimal zone. So yeah, that to say, during my exercise, when I don't have, I guess I can just back up. So when my arm was at this point of the bicep curl, the amount of strength I had in contracting it would be less than when my arm was at here, this area of the bicep curl, because there's a greater amount of overlap between the myosin and actin filaments, which means more of them are contributing to pulling. Because the more myosin and actin filaments contributing to the movement, the stronger the pull is going to be, because there's simply more of them. So the greatest amount of strength in contracting would be about right here, I think, is the most optimal for bicep curls, is about 90 degrees. But yeah, that's just a really quick one. So, to further explain the science about it, because I feel like this one's kind of short otherwise. Actually, no, it's really good in 5 minutes. So, when the muscles wants to contract, they have a actin and myosin filament. On the actin filament, those actin binding sites, and these actin binding sites have a set of two proteins on them called troponin and tropomyosin. Tropomyosin is attached to the actin binding site, and troponin is attached to tropomyosin. So if I can just, aha. So you have a thicker and a thinner filament, and on that you have, I don't know how well that's going to pick up. So you have your actin, no, you have your myosin and you have your actin, and you have troponin and tropomyosin. So you have the actin binding site on actin, actin binding site on actin. So myosin is going to want to attach to this actin binding site. So ACB and myosin. So ACB representing active binding site, myosin representing a myosin head. So it's want to go attached to them. But troponin and tropomyosin are going also want to attach to it, specifically tropomyosin. So when tropomyosin is going to be the default one in an uncontracted muscle, which is a protein that's attached to an actin binding site. So to get tropomyosin off of the actin binding site, we bind a calcium ion to C+. Again, I don't know how much this is actually helping, but we bind a calcium ion onto troponin that pulls tropomyosin off of the actin binding site, which allows myosin to bind to the actin binding site. And from there, what happens next is adenosine phosphate, which is attached to tropomyosin. No, adenosine diphosphate and phosphate ion is attached to myosin. They are released from the myosin, and using that energy, it pulls back, which moves the actin binding site this way. So it's really, the myosin is kind of set in stone. It pulls the actin, and by pulling the actin, it also pulls myosin itself. So these two things are actually pulling towards each other because of myosin is kind of pulling it towards itself. And because there's another myosin on the other end also pulling it towards itself, it has a compression effect as the alternating layers of actin and myosin all pull each other towards each other, which makes the total length decrease and thus contract. So then if we want this to stop, then what happens in the contraction would be ATP would rebind onto it. We bind onto the myosin head and then get broken down by ATPase. By breaking it down, So by binding ATP to myosin, the myosin lets go of the actin binding site, then it breaks down the ATP, which recocks the head, puts it back into the forward position, because like I said, it pulls it back. So then it lets go and cocks back forward. So pull back, adenosine triphosphate binds, lets go, adenosine triphosphate denatures or gets broken apart, and it recocks. And then adenosine, and once it's recocked, that allows it to bind again, and then adenosine phosphate and phosphate ions are released, pull back, adenosine triphosphate attaches, a release, and then it gets broken down, COX again, adenosine phosphate. It then binds to a new actin binding site, and then it releases adenosine phosphate and phosphate, pull back again, and it's just going to continue this 3-step layers. I hope that makes sense. But yeah. So to stop that, the contractions from happening, we let go of this calcium ion onto troponin. And what's happening is that calcium ion is continuously getting let go, but is immediately replaced by a new calcium ion. Not immediately, those is certain time frames. So the calcium ion's eventually going to be expended, and once it's expended, it lets go, which allows a new calcium ion to attach onto it. But if we stop adding these calcium ions to troponin by pumping the residual calcium ions back out of the cell, because we introduce these into the cell through cell signaling by the nerve impulse, which signals muscle contraction, is what allows calcium into the cell, calcium ions. And so without this calcium ion, troponin is going to stop affecting the structure of tropomyosin in that way, and it's going to stop affecting the structure of tropomyosin to prevent it from attaching to the actin binding site. So basically going back to normal is a better way to say it. So now that tropomyosin is back to normal, it's going to attach to the actin binding site because it has a higher affinity for it than the myosin head. So once that myosin lets go after the adenosine triphosphate is broken down, well, once a ATP is attached to the myosin head, tropomyosin is going to attach to the actin binding site, and that prevents any further binding of the myosin head. And with that, the contraction is stopped. Another thing that can happen is just the prevention of the breaking down of ATP, because you need ATP to bind onto the myosin to let go of it. So if no ATP binds to this myosin, it's just going to hold that contraction level. So that's where you get muscle tone, by holding a specific amount of contraction. I feel like I talked enough. That should be the end of it. It's like 13 minutes long already. But yeah.